Alright, hey guys, welcome back to my channel. So we will discuss a bit more about matrices as linear transformations. So as we all know, uh, you have a vector v, right, of dimension, let's say n by 1, and you apply a transformation, a matrix T, on this vector, and you get some vector which is b of dimension, let's say m cross n. So the dimension of this T transformation matrix will be m cross n, right? So what T is doing is T is transforming V into B, means basically T is a function, can be thought of as a function, the matrix T, which maps from Rn to Rm, right? So this is what matrices as linear transformation is. But the question is, what is TV? So if you have a vector v, you multiply that with a matrix T, what is this thing? So let us take an example first. Let's say I have 1 0 and then I have -1 and 1. Let's say this is my transformation matrix T, and I have a vector, taking the simplest case, 1 1. This is my vector v, right? So what TV is, TV tells me the vector v in a space which has basis vectors c1 and c2, means the c1 and c2 are the columns of the transformation matrix. So what do I mean by this? Well, I said that TV is nothing but the vector in a space that has basis vectors c1 and c2. So these are the two vectors, these are my basis vectors, and this will create a space. So this will, if I subtend this, so extrapolate, then this will create a space, right? And TV is nothing but, you can say, this vector is TV, this vector is TV. Now you can see the TV here by diagram. You can see that TV is nothing but c1 vector plus c2, right? And that is quite evident from this matrix multiplication, because this matrix multiplication whole thing can be written as 1 times the first column plus 1 times the second column, and this column is nothing but 1 dot c1 vector plus 1 dot c2 vector, isn't it so? So what matrix multiplication does is, you have a vector in your original Cartesian plane, means Cartesian plane means here, where the basis vectors are nothing but I and j. In other words, basis vector are the columns of the identity matrix. So this is the plane where we generally draw vectors, right? But after applying a transformation T into this vector v, this will be transformed, or rather mapped, into a space which has basis vectors c1 and c2, and this basis vector and this space is known as column space. Why? Because c1 and c2 are the columns of the matrix T, and the linear combination of these two columns, which means linear combination of these two columns means alpha c1 plus beta c2 will give you the entire column space. So which means that if you in this one, if you take any vector, so right, if you take any vector, we'll have something like this, then yeah, So here this vector will be sum alpha c1 and this is your sum beta c2, right? So any vector here will be nothing but the linear combination of c1 and c2. So think you can think of this as c1 and c2 as, let's say, I naught j cap, I naught cap, and then j naught cap. So basically I have taken my v vector is 1 1. Now if you take any vector, random vector, let's say alpha beta, and you multiply that with this matrix, which is 0 1 and minus 1 1, then this will give you nothing but alpha c1 plus beta c2, right? So in other words, this transformation, what it does is it maps this v vector from our Cartesian plane to the column space of the transformation matrix, right? So that is what linear transformation is. Now, keeping this in mind, let's discuss about MLPs, neural networks. So let's take the simplest case. You have two nodes, right? Two nodes, and let's say three hidden nodes in the first layer. So this is your layer 1, this is your input layer. I'm referring this input layer as, denoting this input layer as I. So, and this is known as multi-layer perceptron because you have layers of different perceptrons. So this is your one perceptron, this is your another perceptron, and this is your another perceptron, right? You have three perceptrons together which shares the same input. Now, as you know that perceptron has some weights, so let's say this is your 1 2, this is node 1, node 2, and this is node 3, right? So the weight of this matrix will be W11. This is, let's say, W21, since it's connecting to the second node of the input layer to the first node of the first layer, right? Similarly, the weight will have W12. Let me just write the matrix properly. Yeah, let me just write the weight matrix. The weight matrix will be something like, let's say, W11, since 1 is going to connect to 1, then W12, and then W13, right? Then you have W2 connected to 1, W2 connected with 2, and you have lastly W2 connected to node 3. This is your 2 by 3 weight matrix. This is known as weight matrix. And yeah, usually perceptron has an activation function, but in our case we are not considering any activation function, right? So that being said, let's see the input vector. So input vector is x1 and x2. Let's say this is my x1 x2 input vector, or let me write it as x1 and y1. Yeah, that will be better. x1 y1 is my input vector. So what will be the output of this network, of this simple network? Well, node 1 of layer 1, let's say node 1 of layer 1, right? Node 1 will give you what? x1 times w11, right? Plus x2 times what? w21, right? Similarly, node 2, this one, node 2 will give you x1 times w12 plus x2 times w22, and node 3 will give you x1 times w13, x2 times w23, right? Now since input is a vector and this is a weight, so output will also be a vector. This will be my output vector, right? This thing I can write this as summation of two separate vectors, and those two are x1w11, x1w12, x1w13. Similarly here this will be x2w21, x2w22 and x2w23. Here I can take all the x's common, and this will be this vector multiplied with scalar x. Similarly here I can take x2 common and I can erase this whole thing, right? Now this thing, entire thing, we have seen from matrix multiplication that this thing can be written as matrix multiplication of x1 vector, x2 vector with w11, 12, 13 and w21, 22, w23. This has shape 3 cross 2, this has shape 2 cross 1. So this multiplication is valid, right? So this is what the output of this small neural network is, without any activation function so far. So if you now you can clearly see that this matrix is nothing but the transpose of this W matrix, so which means, and let's say this is your x1, this is your x1, then this is nothing but W transpose times x1 vector, right? So this is the output of layer 1. So this is the output of layer 1. Now if you look carefully into this equation, if you look carefully over here, then this is a matrix multiplication, right? And what we have seen from our discussion previously, that this vector x vector will be mapped into the column space of this matrix, which is W transpose, right? So here you will be having column space in R3, and in that space this vector will be mapped into that space. Means all the points, let's say you have a data set, x has, let's say, x1, y1 and x2, y2 and x3 and y3. This is your data set. Then all these 3 individual points will be mapped into the column space of W transpose, like W transpose matrix. So that we can say, right, from our discussion over here, like that this is nothing but a matrix multiplication, and neural networks has weights and you multiply this in this fashion, right? So this is what matrix multiplication is. So can we say that given an input vector, and yeah, you can, in here you have, let's say, data set of 2 by 3. So you have your W transpose vector, which is dimension 3 by 2. You multiply this with entire x, which is 2 by 3. You will get nothing but the output of these individual vectors. Let's say this is your v1, v2 and v3. Then you will get output of ov1, let's say ov2 and ov3. These are the output of individual vectors, right? So this is one way, like you are computing the output of the entire data set in one go, in one shot, as a matrix multiplication. So this is basically what you are doing is you are like mapping this v1 into the column space of W transpose. Similarly, you're mapping v2 into the column space of W transpose. So all these data points will be mapped into some space. You are doing a linear transformation onto it. But since this is linear transformation, then this also means that the space between, or the orientation of the points, these 3 points, will be maintained. Means let's say you have your 2 blue points over here and then 2 red points over here. Then after applying linear transformation, you might get 2 red points right over here, and blue points can be in this fashion, right? Consider this thing. So this like applying a linear transformation into all these points, you might get something like this. This might happen. This is one of the possibilities. But with linear transformation, you will never get like two blue points over here and then red points over here. This cannot happen with linear transformation. For that, we need non-linearity. Means we need non-linear transformations. And non-linear transformations we can get by passing this entire output through a non-linear function. So that can be tan inverse x, let's say tan inverse x, or let's say sigmoid function or ReLU or something, which will apply non-linearity into this space. So whenever we are applying some non-linearity, then no longer this orientation will be preserved. The orientation of these points will be preserved. In that case, you might get this type of orientation in the data set. So based on this, what I think neural network actually does is it takes the input vector and maps it into the column space of the weight matrix, and it tries to figure out the perfect column space, since we are changing the weights. And in gradient descent, what we have learned, that we can change these individual weights. So changing these individual weights will create different column spaces, right? And it can happen that the rank of this W matrix, rank of this matrix can be 1, right? In that scenario, what will happen is the column space will be a single line, right? So this is basically my understanding. Based on my understanding, this is how I believe that the input vector is mapped into the column spaces, and so on and so forth. And if you increase another layer, if you add another layer to it, let's say 2 nodes like this, then this will have its own weights. Let's say weight 2, right? So what you will do is that weight matrix, you will multiply the transpose of it. You will multiply the transpose of this with the output of layer L2. So this is the output of layer L2, this one. So you will multiply W2 transpose. And definitely after applying a non-linearity, means the ultimate, let's say your activation function, now you have activation function on layer L1, which is, let's say, tan inverse x. You use your activation function, then the resultant output will be nothing but your W2 transpose times tan inverse of W transpose x1. This will be the entire output of this network, right? So that is what I think neural networks does. Actually, it just maps the entire data set into different spaces. As basically it can be thought of as searching for the space where this set of points can be linearly classified, or will be much easier to classify. That is, I believe, what we are doing actually. So this was my take after learning linear algebra on neural networks. Yeah, so if you believe that this idea is wrong, then feel free to comment down in the comment section below. But I think, based on my knowledge of linear algebra, this is what it should happen. That is what my belief is. And also it also explains that why do we need activation functions on the like tan inverse function or sigmoid function, because without activation function, if you multiply, let's say, a E matrix with X, then E1, and if you again multiply E2 and then again multiply E3, then this is same as multiplying a single matrix with X1, right? That was it. That was my take on matrix multiplication and the weights of the neural network. Alright then, that being said, adios.